Hello, everyone. Welcome to the next webinar in our monthly office hours series. Today, we'll be talking about polymer 3D printed parts, specifically the material options. So before we get started, though, I wanted to talk about, we have a couple housekeeping items. As you'll have noted when you joined the webinar, when you registered for it, that you were requested to submit some questions about what you're hoping to get out of the webinar. I've used those to specifically craft the details that you'll see coming through here, but we definitely want to make this conversational. So please be sure to go ahead and submit your questions in the Q&A as we go along. And we will be sure to get to those as we go along. So we won't wait till the end. With that said, I'd like to go ahead and introduce the speakers for this month's webinar. We have Jonathan Wilkie from GoProto, and we have Alex Knox from Re3D Tech. You'll notice we have one from each of those companies. GoProto and Re3D Tech have recently combined forces under core industrial partners to form one of the largest and most complete custom rapid manufacturing companies in the US. But I'm going to let Jonathan here introduce himself and explain a bit more. Go ahead, Jonathan.
Hi, welcome. Glad to be joining everyone here and looking forward to this conversation. So I'm Director of Eastern Sales with GoProto, been with the company since its founding in 2017. Located in South Carolina. My background is in product development. I've been on the side of the fence of doing design work when I started my career, then moved into actually running machines as well, and then been working on the sales side for many years. So I sort of understand the full facet of product development from start to finish.
And my name is Alex Knox, and I graduated from UIC with a degree in mechanical engineering. And I've been here at Re3D Tech for about 1.5 years working with the HP and Markforged technologies.
Great, thanks, Alex. So first off, we'll go through the topics we're going to be covered today. As you'll see here, we're going to go through a real quick overview on essentially Re3D Tech and GoProto's processes for ideation all the way through to production. We will discuss the printer technologies. There's 5 primary polymer printer technologies, 3 of which we will be discussing today. We've then split the materials that are used within these technologies into 6 various categories. Within those categories, we will then discuss the mechanical properties, their uses in extreme environments, their cosmetic appearance, and then finishing options. As I mentioned, definitely feel free to ask questions as we go along. I also have noted some of your questions that I will be contributing as well if we do not get to them. So with that said, let's kick it off with Jonathan here.
So this slide here basically is just a quick overview summary of everything we offer as a company, and being part of Re3D Tech now just gives us much more capabilities, much more resources, especially on the additive side. But as you can see there in that first section, engineering and DFAM, so DFAM stands for Design for Additive Manufacturing. That really follows the entire product life cycle from ideation through prototyping all the way to production. And we can really help with that. We have engineers on staff to help with that for not only conventional processes, but also as well as the additive world as well, for if you're looking at doing additive manufacturing for production. Concept models is more of a ideation standpoint. It is at the beginning of the product development cycle, taking a napkin sketch and then using it to create some type of concept models, so you can then look at moving forward. And if it's a valid idea, form models, that kind of thing is on the concept side. 3D printing, as you can see there, is ideation through prototyping. 3D printing is more the onesie twosie aspect, 5, 10, that kind of thing, where you are trying to see if the ideas you're coming up with are valid and you want to move forward with them, as well as on the prototyping side where you're doing true prototyping and development and R&D work. Urethane castings, that can be on the ideation side, but it lends itself more to the prototyping and low volume production side of things. We call it urethane castings. A lot of people call it RTV molding. You're basically making a silicone tool around a master pattern of the part, and then you cast a 2-part urethane into that silicone tool to produce the part you're trying to achieve. And that can be very close to injection molding quality parts from a standpoint of finishes and materials. Now, accuracy and tolerances is a different story. CNC machining, we use that a lot for prototyping through production as well. We can machine pretty much anything you can imagine. I tell people all the time, if we can machine magnesium, we can machine pretty much any material you can think of, because if you know much about mag, if you got to machine it pretty slowly, and then if it catches on fire, you better grab what you can grab and run. So the prototyping side of it, a lot of people want to look at the actual materials they're going to use for production, and then of course moving into machining for production volumes. Tooling, molding, that is the injection molding side of the business, where we do some prototyping, but it lends itself more toward bridge tooling as well as production tooling. We don't get into real high volume molding, but we do get into low to mid volume molding, and for just about any material you can imagine. Sheet metal, that's if you're not familiar with the process, that's basically taking sheet stock of some type of metal, aluminum, you name it, and then you cut it out, laser cut it, or you stamp it and then you form it to make a particular type of part. Use a lot for enclosures, electronic enclosures, that kind of thing. We do it for prototyping, onesie twosie, through production as well. So we can help you out with that. And then additive manufacturing, that is the terminology used for production 3D printing, if you will, when you're getting into higher volumes, not just the prototyping side. So that lends itself for prototyping, but as well as production. We have some customers where we've done several thousands of parts in the additive world, where traditionally it would be machining or injection molding, but they realize they can use the additive for that process. And then finishing goes across the board. We can do pretty much whatever you need, from cerakoting, painting. We'll get into that down the road as well, but we can do all kinds of finishing options for each one of those processes.
Great. Do you want to just do a super quick overview of these so we can get on to the materials themselves?
Yep. So these are the printing technologies we'll be talking about. The three blue ones you see there are the ones that we have, and we focus on. DLP and SLS are the other two in the industry. Multi-jet fusion is a powder bed technology that uses a binder and then UV light to solidify it. It's a thermal based process. FDM is your extrusion based technology that you see pretty regularly. It can do production, but this is ones you can buy off of Amazon for $500, but there are also production machines out there for, you know, much more than that, six-figure range. Stereolithography, this is the original of the 3D printing technologies developed back in the mid-80s. This uses a photopolymer and a UV light source, a UV laser, to then solidify the photopolymer and build layer by layer, like all of these are, to produce a part. DLP is basically opposite of SLA, and then SLS is very similar to MJF, but uses a laser instead of a binder material.
Great, thanks, Jonathan. So one of the questions that got submitted is, are there different printers for different materials? So we've taken these available materials and we've broken them into 6 categories to discuss today. So for the purpose of the conversation, we can break them up across the three different printer technologies that Jonathan just explained. So photopolymers are a liquid. It's often called vat photopolymerization because it's a liquid with a laser. The MJF has 2 different categories that we're going to talk about: the rigid nylons and polypropylene, as well as elastomers. Then we break the FDM up into 3 different technologies. We have Ultim and Antero, ABS, etc. And then again, the rigid nylons. Those are filaments, so they're going to behave differently than the powder technologies and the liquid technologies. So that's why we've split up the rigid nylons into 2 separate categories that we'll be discussing. That said, here's the material specifically that we're going to get into. And as I said at the very beginning, we're going to take each one of these categories and talk through the mechanical properties, the uses in extreme environments, the appearance, and finishing. So to start stuff off, we'll start with mechanical properties. Jonathan, do you want to start with the photopolymers?
Yeah, sure. Love to. So the photopolymer side of thing with stereolithography, the mechanical properties are not great on this material because it is a photopolymer. And as you can see there, your X, Y, and Z strength is not great. In fact, I got some parts here. I'll show you some examples. The stiffness and modulus isn't great. Elongation is really not much at all. And impact strength not much at all. Once again, because it is a liquid photopolymer. So the advantages of it, though, is it is very close to injection molding from a surface finish standpoint, as well as accuracy. And here's one part here that is an SLA part out of the Acura material. And you can see here the surface finish is great, accuracy, details are really, really nice. But you can see this little clip here has broken because it is a very brittle material. So you wouldn't want to use it really on any type of actual mechanical testing. Rigid nylons and polypro. This is out of the multi-jet fusion technology. This material works really good for any type of mechanical testing, and that's why a lot of people are really starting to look at using it for true additive manufacturing to replace machining or injection molding. The durability and strength is phenomenal on this because it is a nylon material. So you can imagine how rigid nylon 12 is. And you can, I mean, I've taken parts and thrown them up against a brick wall and they've been fine. The stiffness and modulus, depending on the way the part is oriented in the build, because it is a powder bed technology, and the features that are designed in the part, they can be good, but there are things you have to take into account. So for instance, this part here, this is a multi-jet fusion part, raw material. This clip works really well here. And you can see the bend is really nice, but the way we oriented it in the build really helps with that. So that's one thing to take into account. Elongation and impact strength is great as well because it is nylon. Then elastomers. I got a really nice elastomer part that I'm going to show you here. So we run TPA and TPU. One's 88 Shore A and the other one's 95 Shore A. Durability and strength is good because it is an elastomer. Stiffness and modulus is good. Elongation is great. Impact strength is good as well, once again, because it's an elastomer. So this is a TPA material. It's really the best elastomer material I've ever seen on the market in the 20 plus years of being in this industry. So you can see the rebound, the bounce back is really, really nice on that material and works great from an elastomer standpoint.
Great, thanks, Jonathan. Alex, do you have anything to add, or perhaps you can actually answer one of the questions we have here?
Yeah, sure.
Is there a material stronger than the MJF PA12? Brackets, shock loads are a concern, but so is rigidity.
There is. So actually in the anisotropic side, funny enough, we do have the Markforged technology where we can add fiber to reinforce nylon, and that'll give you higher stiffness and just a stronger part overall than you can get directly out of MJF part.
Great. Do you have anything else to add on the MJF, or do you want to go ahead and start continue with the rigid nylons or the other materials there?
Well, I guess just that with an MJF part, it's very similar to an SLS part, or even in some cases injection molded parts, but you can get them much faster without tooling. And so that's the real big advantage there with those. And then as far as the FDM side, you can also have very fast turnaround with those parts and also get the strength and stiffness that you need for tooling or shock loaded parts.
One thing to keep in mind, just to add to that from the FDM side, is orientation is a big deal in FDM. The way you orient the parts, depending on the features that are critical, determines how well those features are produced. So your Z-axis is usually your, I don't know how to phrase this. Your Z-axis is usually not your best axis when you're printing parts in the FDM technology.
Yeah, and as long as you keep that in mind, you
OTEM
can
or the
actually,
ABS. Oh, sorry, go ahead.
sorry, go ahead. You can get around that depending on how you orient the part though.
Sure.
And again, with the added fiber, sometimes you can increase that. But
Yep.
yeah, you're still limited in the Z-axis in FDM.
Right. Right. So moving on to the extreme environments, we had quite a few questions that came in on this in terms of what materials are best for which chemical UV exposure and such. Do you want to start again, photopolymers, Jonathan?
Sure. As you can see there, you see 3 big red X's on all 3 of those categories for photopolymers. So you're not going to use photopolymers. You're not going to use stereolithography really at all in any of those type of environments. It is a UV sensitive material. So an example of that is if I were to take a plastic cup and dipped it in the vat of an SLA machine and pulled out a cup full of the SLA liquid photopolymer and put it outside in the sun, then and let it sit for a while, it would and come back, it would be solid. So it is not good for UV exposure or any type of chemical resistance at all. But once again, there are other advantages. There's really one thing to remember as we're going through this. There's no one perfect technology for any additive. They all have their places and their advantages. It just depends on what you're looking for. Rigid nylons and polypro out of the multi-jet fusion process, extreme temperatures is great because it is nylon. I think the heat deflection temperature, Alex, you might know better than me on this, but I believe it's 90, is it 90 C, 75 C, somewhere in that standpoint.
It's right around there. I've had some parts that I actually don't know the conversion to C offhand, but 200 to 250 F.
Yep.
We've seen parts last in that temperature range.
Exactly. Chemical and UV exposure, it's great once again because it is nylon. It's nylon 12, and then if you slice that part in half, if you slice one of these nylon parts in half, it's completely solid, so you don't really have to worry about seepage from a chemical standpoint. It is only HB rated. It is not V0. There are other nylons out there that are V0 for flame rating out of the powder bed technologies. And then elastomers, basically the same thing as the rigid nylons and polypro, as you can see there in the chart. Once again, it is only HB rating for the flame rating. Ultim is your best when it comes to flame rating. As you can see there, it is V0. Here's an example of an Ultim part. Ultim is really used a lot in the aerospace world because of its flame rating. But once again, as we talked on the previous slide, it is run in the FDM technology. So your Z-axis is something you have to take into account when you're printing parts with critical features.
Yeah. And
okay, so we have quite a few questions from the submissions when you registered. Go ahead and submit additional ones on the Q&A. I just answered one, but I would like to get to some of these other ones. I think one of the most important ones to answer here, which materials are best for end use parts versus which ones are best for prototyping. Either one of you go ahead and address those two.
Well, for the FDM side, you can get a pretty quick prototype right away, even if you're not going to get that strength in the Z-axis, but if you just need a piece of plastic that represents the shape of the thing you need, you can get that really fast. And then from my perspective, as far as end use parts, the MJF technology with the nylons, it really can't be beat for cost and speed compared to the other technologies, as well as you can still get a fairly good resolution out of those parts with some finer details. Not quite as good as SLA, but still fairly good resolution.
Maybe one thing you can address is I know this varies a lot, but the approximate volumes you can get out of these technologies, and realistically, I know that's in the thousands for MJF, whereas SLA, I think you probably wouldn't reach that point. Unit volumes, excuse me.
Yeah, with SLA, you can, just depending on, once again, it depends on the application for all this stuff, but SLA, the large platforms, they have a large build tray. So one of the largest is 24 inches in your X, 29 inches in your Y, and 21 inches in your Z. So small parts, medical parts, you can get a pretty good bit of volume out of SLA. Big parts, consumer parts, you're not going to get a lot out of SLA for that. That lends itself more towards the MJF side of things. You're right, Kristen, that MJF is going to be your best. It's the fastest on the market, and it's the most cost effective, as Alex said a second ago as well, from a standpoint of looking at it at a true manufacturing type application. We've had some customers that are in the robotics world, and we've run 6,000, 9,000 parts for them over the course of a couple of months. And that is a true manufacturing process. They actually looked at replacing machining with MJF for many different reasons, cost being one of them, and then the part performed how they wanted. So once again, it's application dependent. Now, on the MJF side, you're not going to, if you think you're going to have, if you have an injection mold and you think you're going to replace it with millions of parts coming out of MJF, more than likely that's not a good application. You're going to want to stick with the injection molding side. But if you got 5,000, 10,000, possibly 20,000 parts in that ballpark, yeah, it's great. MJF is a great application and great tool for that.
How about, let's talk about size of parts. Which materials are best for large parts? How big can they be printed? And then a secondary question, which I want to lump in there, is, can any of these materials be ultrasonically welded together?
Go ahead, Alex.
Yeah, so for MJF, you're limited to about 13 inches cubed, roughly. We can get some parts if they're very long, skinny parts, and the max dimension is about 18 inches. We can get away with it sometimes, going corner to corner in the build. And then with any of the FDM technologies, nowadays the sky's the limit for size. But obviously you're not going to get as many parts, so it would be limited to like the 1 to 10 quantities probably.
Yeah, and size, to add on to that, size out of the FDM, we do have a machine, this FDM 900 by Stratasys, and the build platform on that is 36 inches wide, 24 inches deep, 36 inches tall. So you can do very large parts in that system, or a bunch of small parts as well. But once again, that is FDM versus MJF. And then I explained earlier on the SLA side, the actual build platform for that. And then ultrasonic welding, great question. Yeah. MJF works great for ultrasonic welding. The other materials, not really. The other processes, not really, because of the way it builds. But MJF works phenomenal for ultrasonic welding. We've had several customers actually ultrasonic weld PA12 parts. Now, we haven't had anybody do it on other materials that I'm aware of, but the unfilled nylon 12, they've done it. They've ultrasonic welded parts, and it's worked great. Treated just like regular plastic, regular nylon plastic.
I'll add to that too and say that you can also effectively epoxy the nylons together. If you do want a bigger part, if you section it and then glue it together after the fact, you can get larger parts through that.
Yeah, great point. Great point.
Right. I want to go back to the previous slide. Someone submitted a question. Do you have elastomers with lower hardness?
Currently, no, we do not. The challenge with printing elastomers is it can get like spaghetti noodles if you're not careful, or on the powder bed side, it can get very, very gummy. So the softer the durometer is, the more of a challenge it is to print. The lowest durometer I know of right now is really the 88 Shore A TPA material that you see there on your screen that we currently run, and that's the softest. Now you can do some stuff from a design perspective to make it feel and perform like a softer material. So you can actually add in lattice structure that will make it feel softer and more squishy. And if I had one nearby, I would show it. But sorry, I don't have one. I can probably find one here in a second. That will make it perform and feel softer. We've had some customers actually print parts out of the TPA with a lattice, internal lattice for armrests, and it does feel softer from that perspective. But the shore hardness directly out of the material, no, that's the lowest you can get.
Right. Let's move on to the cosmetic as printed appearance of these parts.
Sure. So photopolymers is going to be the best, as we've already said. This is once again another photopolymer. This is the photopolymer here I showed a minute ago. This is SLA. You can see it's nice and smooth finish. It is going to be your closest thing to injection molding finishes that you can get out of all of the 3D printing technology. And we can also do clear. This is a clear Accura 60 material that you see listed there on the screen that has been clear coated. One question that comes up with about clear all the time is it optically clear? Straight off the machine, no, it's not optically clear. It comes out cloudy. We have to do some polishing and clear coat it. And then as soon as you clear coat it, the true optics of it are thrown out the window. It will still transmit light, but it's not going to be like an LED lens, if you will, that's molded out of acrylic. You're not going to get those same type of optical clarity out of it. The nylons multi-jet fusion process comes out of the machine, this sort of gunmetal gray. In fact, I love it. I love the way this looks, but this is how it comes out of the machine. And then we dye it black primarily. That's what most customers want. The dye is really a cosmetic thing more than it is anything. You can see the two difference there from a finishing standpoint. But we can paint it, we can Cerakote it, we can do all kinds of stuff, and we'll get into that as well from us on finishing side. Elastomers is really the same thing as MJF. It comes out of the machine, or as a PA12, it comes out of the machine, this color, and then of course this is an elastomer TPA part that we can then dye black.
And then one thing I'll add to the nylons and MJF, we can do full color in-house as well.
Mm.
So we can do full colors based on an RGB code, or if you have a file with multiple colors in it, we can print that as well. The only color I would say it does kind of poorly is reds. Those don't turn out as well, but whites, blues, and then green comes out really well. So that's another option for surface finish.
How about the FDM materials?
Yep. On the FDM side, the material comes in different colors. So like Ultim, you can see it's sort of this gold looking color. We can do green, black, blue, red, and it all comes with that color. There's multiple options on the Ultim side. But the black or the natural color is the most common, like I showed on the Ultim part just a minute ago.
So one question that was submitted that's not on here is, what about the as printed surface finish of these various materials? Is there variance there, ones to consider if you want better surface finish?
Yep, your best surface finish is going to be SLA. That once again, I'll try to show it the best I can here. Let me see if I can compare. So this is FDM. You can see it's a little more granular because it's a powder bed technology, whereas this is SLA. You can see it's more smooth because this is a liquid photopolymer. You can see the top there is shiny. That's the top surface. That was the last surface to be printed. So SLA is going to be your best from a surface finish standpoint. That's why it's used a lot in marketing study models, customer facing parts, industrial design models, stuff that you need to paint and look like a finished injection molded part. The MJF, you can do a lot from a finish standpoint, but directly off the machine, SLA is going to be your best option.
And any of the FDM stuff is probably your worst as far as surface finish, but
Yep,
there are
no
some
doubt.
post processes that we can apply to that to make it better.
Yep, we can. So this is a good example of an FDM part. Let me see if I can get it where you can see. Maybe you can see the layer lines here is just not great. But like Alex said, and this one might be able to see a little better. Like Alex said, we can do some stuff to help finish, to help with that. One of the things we can do is you can smooth FDM parts. This part here is smooth, even though it's off the MJF system. So you can see surface finish is smoother and it's a little more shiny. So we can do that on the FDM side. We smooth parts on the MJF side as well, which is what I just showed here. So that helps with the finishing is also on those technologies.
So we just have a quick question. Can FDM handle elastomers?
You want to take that one, Alex, or you want me?
Yeah, it actually can. And Markforged actually just recently released their TPU material, which is the same type of TPU that we have on the MJF, but again, it just won't have the same surface finish as the TPU coming off the MJF printer.
Could you maybe dive a bit deeper into that in terms of why you would do an elastomer with FDM versus an elastomer with MJF?
I guess quantity. If you're only looking for 1 or so, or 1 to 10, FDM will probably be cheaper and just be faster. Whereas if you're looking for over 10, 50 to 100, MJF is going to be your go-to.
Great.
The
And then
challenge-
Jonathan's question, I think,
Sorry.
Jonathan, you touched on this at the very beginning, but it was submitted as a question. Are the printed parts machinable?
Yes, they are. You can treat them just like in any of these technologies, quite frankly, you can treat them just like billet plastic you would buy to machine. You can put them up, chuck them up on an end mill and machine it, no problem. You can put inserts in them, helicoils, you name it. You can treat these just like injection molded or billet machining that you would buy block of. Now you do have to be a little careful with the SLA once again, because it is brittle. So you have to sort of machine that a little slower and give it a little bit of TLC. But the FDM and the MJF can handle pretty much whatever you need.
Did you have a part to show there, Alex?
Yeah, sorry, I don't know if it shows up very well, but I did machine this one on a mill. You can kind of see the shinier surface. So these are solid parts that have a solid cross section. They're also, you can use them in vacuum parts. So if you have air channels you can put through it, it will actually hold air to smaller vacuums. And then also MJF parts are watertight as well.
Right. Well, I think we can move on to the finishing options now. So we've got these 6 finishing options, but we've broken them into 2 categories. We're going to start with the finishing options that are for cosmetic purposes only. Do you guys like to touch on these 3 here?
Sure. So dyeing on the MJF side, once again, it comes off the machine like this. So it's a gray color and it's dark. You don't want to dye it light colors because that gray will bleed through. So like we said, we typically dye parts black, but you can see in that picture there, we can do a dark blue, dark green, a red color as well. Hydrographics, you all probably are familiar with hydrographics. It's taking apart, putting a film of whatever design you have on top of the surface of a water in a tank and dipping the part in there. It just gets the external surface, not the internal surfaces. So we can do that on hydrographics. That's strictly cosmetic. Painting, we can paint parts pretty much whatever color you need. We can match colors as well. And you can, put them in a paint booth and do some nice finishing work from a painting standpoint. Now, with the MJF side, the MJF parts, with them being rough, we do have to do some pretty heavy duty priming before you paint it, because once again, it is a little rough because it comes off a powder bed technology. So if you want it nice and smooth, like it would be off a compared to maybe injection molding, then or machine part, then we do have to do some prep work from a standpoint of priming the parts.
Yeah. And one of the potential drawbacks, I'll say, of dyeing is that sometimes the dye can actually leach out of the part. So if you have your MJF part near like something white that you don't want stained, just go with the natural gray or do the painting option.
Very true. Good point.
All right,
So
you want
metal.
to touch on the performance ones?
Yep. Me or Alex?
Either one of you. Go ahead, Jonathan.
All right, metallization. This has really 2 classifications. Really, it's used for, and I wish I had some good parts to show you, but unfortunately I don't. Metallization is used for 2 things. One, cosmetic, so that's primarily chrome plating, or you can nickel plate. Nickel plate is good for cosmetics. It's beautiful when it's done, but it also adds a lot of strength characteristics to the part. And you're primarily going to use metallization on SLA parts. The reason for that is as soon as you metallize a part, it will pop out every single defect in the surface. And SLA, like we said earlier, is the smoothest surface straight off the machine, the closest thing to injection molding surface finish. So you want to really try to stick with SLA if you're going the metallization route from a cosmetic standpoint. Cerakoting, if you're not familiar with Cerakoting was really developed for the firearms industry. You see it a lot in different firearms. People want to customize their pistols or rifles or shotguns, whatever the case may be. That's where Cerakote was primarily developed for. It it goes on like a paint, but it's a thin layer of ceramic. And this part, this orange part right here, this actually is Cerakoted. So the nice thing about MJF is we can Cerakote parts because the way the process works is we spray it on like you would a typical paint, and then you have to post bake it. So because MJF is nylon materials, it'll handle that post baking temperature process, whereas SLA won't. So you can't Cerakote SLA parts. And then vapor smoothing we touched on a minute ago is basically you take a part, you put it in a tank, and you set the parameters. The tank does its magic and it smooths the parts out to give you a shiny finish like you can see here, versus that which is a little more rough, coarse type finish that would be standard off the machine.
Yeah, and so something I'll add to that too is it does make the surface easier to clean, so it can be used in skin contact applications. Some of the MJF parts can be, specifically the PA11 and the TPU.
Very true.
And with vapor smoothing, isn't there also studies that have shown an improvement in impact strength?
Yes, especially for the elastomers. The elastomer materials, and we have white papers on that stuff as well, and it's all online. So if you guys are interested, if you all are interested in that, reach out and we can help you out with that. But the elastomer materials definitely improves the elongation and the mechanical of the part and the performance of the part once it's smooth. You really don't want, on the MJF side, you really don't want to run elastomers without smoothing it, because you just won't get the kind of performance you're looking for.
Yeah. It also really helps with the water absorption for specifically the elastomers.
Very true.
Great. Were there any, I forget if there were some numbers regarding the metallization. Was that something that you had to share, or was that?
Yeah, I don't have those offhand.
Okay.
We can get them to it if people are interested in them.
Okay. We do have a question about the metallization. How thick is the metallization? And secondarily, has there been any testing on RF blocking for parts that contain antennas?
Yes, you can RF block them with going the metallization route. That does work. That's really about the best way to do it with 3D printed plastic parts. And then as far as thickness of the coating for metallization, it depends on the process. So if you go chrome plating is going to be thinner than nickel plating. Chrome is going to be in the ballpark of about 0.003 or so per side. Nickel plating is going to be a little more than that. It's going to be pretty much double. It's going to be in the ballpark of 0.006, possibly even 0.008 per side, because with nickel plating, you have to put on a thin layer of chrome, and then you have to, thin layer of copper, I'm sorry, and then you have to put on the layer of nickel on top of that. So it's a two-step process that then causes the thickness to be about 0.006 per side.
Okay, with vapor smoothing, how much dimensional tolerance does it change in dimension?
It really doesn't alter it too much. I would say maybe 1 or 2 thousandths at most. You'll notice more of a difference in the fit of parts if you have two MJF parts fitting together and they're vapor smooth, they'll have a bit more friction actually and kind of tend to stick if it's an assembly. But as far as the actual measurement, it'll only change by 1 or 2 thousandths of an inch.
Okay. With that, we are moving on to just any additional questions you have. I have a couple saved from your submissions, but go ahead and put any additional ones in the Q&A, and we'll get to them now as well. One kind of back to the beginning as well. What are the appropriate materials for functional micro parts?
SLA technology out of the photopolymer is going to be your best for micro parts. You're not going to get the resolution out of powder bed technology, so multi-jet fusion or FDM that you need for micro parts. And I have a feeling the question is coming from either a medical application or electronics application, but don't know that for certain. But that's where most of those micro parts are used, is in those two industries, and SLA is going to be your best option, which is the liquid photopolymer. And it can give you the best tolerances. You're looking at, you can get as tight as 0.002 of an inch tolerances on SLA, which you're not going to get that in any of the other technologies.
Okay. I think this is a great question for you guys, both of you. What's the best way to expedite parts?
So we do have a 1-day MJF service. There are some constraints placed on that though. It has to be placed before 2 p.m. Central Time, as well as the size limitation, I believe, is 8 inches cube, basically, and only gray parts. But
Yeah.
you can go onto our website and select the MJF 1 day and get a quote for that.
So to add to that, what Alex is saying is we have a certain build height in the machine for the MJF, and basically we would do half a build because it takes less time. And that's how we can turn parts quicker. You need small parts and then really no finishing. All they're going to do is pull them out of the powder bed. They're going to sandblast them, do a little brush off of the raw material and package them up and ship them out to you. But if you need something quick in your hands to do some testing, to see the part, the 1-day turn option is a great option. If you don't do the 1-day turn, typically MJF is going to be 3 to 5 days for parts to ship out. Stereolithography can be as quick as 2 days. And then FDM, that is very dependent on the actual size of the part because it is a mechanical process, whereas SLA or MJF is a much faster process because that one uses a laser and the other one uses droplets of binder material. But FDM is an extrusion-based process. So the larger the part is, the more the head has to traverse over that entire build platform, extruding out the material to build the part. So it can take some time.
So one question we get often on all of our webinars is examples of applications. Can you, either of you, touch on any of the images that you see here on this slide in terms of why the material was perhaps chosen for that application, or from a material standpoint, what we should know for for any of those applications?
Yeah, sure. I'll jump in there. The first one you can see there, the clear SLA material, that looks like in fact, I know exactly what this part is. I did this part years ago. That is a handheld device for, I think, a patient hospital bed. And there's electronics in there. So they wanted to make sure all the electronics would fit together. So that's why it's clear. Once they assemble everything together, see if there's any interference fits anywhere they need to account for or redesign for. The next part there, I'm not familiar with that part, but it looks to be a printed Mark Forged part. Is that correct, Alex? Is that what that looks like to you?
Yeah, I believe so. I think that is some sort of tooling application. I'm not too sure about that specific one, but that is one of the applications I did want to bring up was tooling. It's something that kind of gets overlooked in 3D printing. Everyone's looking for kind of end use parts, but it has a lot of use in tooling applications. So, I mean, for example, even in-house, I'll make parts out of MJF so that we can post-process parts. So for example, this part we had to drill out one of the cavities here. And this is a very contoured part that would be hard to fixture or put into a chuck to drill it. So we just printed a piece to perfectly go with the contour of the part so that the hole that we were drilling was perpendicular to our tooling. And that was something that we were able to turn around in a day.
Yeah, great application. Jigs and fixtures is something that a lot of people don't think about with this technology because it's historically been for prototyping, but jigs and fixtures out of the MJF, FDM, Mark Forged process is phenomenal. People do it all the time because, like Alex was just saying, you can design fixtures to follow different contours that you cannot machine. I mean, you couldn't machine that. It would be nearly impossible to machine that part and get that exact contour. The next part you see there is a raw TPA part straight off of the machine, which is the elastomer. And that is a hose of some sort. I'm not sure if it's an automotive hose or what it is, but it's some type of hose and that would be the application for it. Now that could go under the hood. You could do some under hood testing for that or higher heat, caustic environment type situations for that. process there in that particular part. So that is a hose, an elastomer hose in that picture you see there. The next one,
I want to say, is that a distributor?
yes, a manifold of some sort. So it looks to be an FDM part of some type of manifold. I'm not exactly sure the application there, but I got a feeling they're mounting that to something. I can see two holes in a little slot there at the very front of the part. Looks like they're probably going to mount that to something and then connect maybe some hoses or some barbs of some sort to it. So what I would imagine is happening there is they're going to do some torquing on that. They're going to put some stress on it. So they need the ABS, or might even be PC ABS there, the FDM technology, to handle the kind of stress and loads that they're going to put on that part whenever they're assembling it or however it's being used.
Yeah,
Let's see.
The next part looks like it's maybe they're replacing a metal part with a plastic part, which again is a really good application for 3D printing. If it doesn't need to be metal, we can provide very robust plastics that can be used in place of metal.
Yeah, and one thing to add on to that, if you think back to the beginning of the presentation when we were talking about design for additive manufacturing, we do have team members that can help you if you're looking at a part that has historically been machined and you want to either lightweight it, make it smaller, whatever the case may be, and you want to look at moving it into 3D printing. A part that is designed for machine does not translate into 3D printing well. You're going to have to do some design for additive manufacturing, and that's where our team can help. Alex can help with that. And we have some other engineers and team members that can help for actually taking that design and designing it, or that machine design and designing it for 3D printing additive manufacturing.
And actually another really good thing about designing for additive manufacturing is you can reduce the cost of your parts pretty significantly. If you have a big solid block that you want to print in MJF, it's going to be very expensive because the pricing is based off of effectively the volume of your part. So if you can reduce the volume of your part while still maintaining all the mechanical characteristics that you need, you can reduce your price by, in some cases, half.
Very, very true. And you can add in latticing to lightweight it, but strengthen it at the same time, which allows you to do stuff that you can't machine it. I mean, there's so many advantages you can do. You just got to sort of retool your brain to think a little bit outside of the box from what you normally would for typical design processes for machining or injection molding. And then the last part there looks like, honestly, a small rotor, if you will, from the back of a motor boat. So I got a feeling that seeing some heat, seeing some pretty high torque, spin rate, that kind of thing. So it looks like that was run in FDM out of the Ultim material. I'm not sure if it's Ultim 1010 or Ultim 9085, but one of the materials is what it was run in. So the application there would be, high RPMs, potentially high heat, different type of environmental areas and environment that it's going to see for, and that's why you would want to go with Ultim. Aerospace applications is great for Ultim as well.
Great. Any other questions from the audience? This is before we move on. Okay. So I want to thank these two guys. If you want to follow up with either one of them, those QR codes will take you to their LinkedIn profile, so you can connect with them directly there, or you could send a general question to quotes@goproto.com. As I mentioned early on, we do this once a month. We do a different topic every month, and it's an office hours where you submit your own questions and we address them as we go. The next one is going to be on Tuesday, March 28th, and it's going to be an entirely different topic, but well within the Re3D Tech and GoProto portfolio is rapid injection tooling from design to inspection. So if you want to go ahead and register for that event, you can use that QR code there, or use the website down at the bottom.